we're back with part 2 of History of the Atom notes. And so kind of taking off where we left yesterday, we were talking about John Dalton and his marble atom and his atomic theory. So what I would like for you to do right now is, if you can, use your notes from yesterday and try to go ahead and fill in, do you know what each person did? And then if they had a model, and what it entailed. So go ahead, use your notes from yesterday. Tell me what Democritus, Lavoisier, Proust, and Dalton did. Hopefully you went ahead and filled those in. Let's talk about it. Democritus was our first idea that atoms even exist. He had no proof, therefore he had no model, and nobody believed him. Aristotle thought that there were 4 main elements, and that's how everything was made up, and so it set us back about 2,000 years. Then Lavoisier came along and started to find some evidence of atoms, and Lavoisier worked on the law of conservation of mass. Okay, he was burning things, doing different chemical experiments in closed systems, and then seeing that the mass always stayed the same. He also did not have a model of the atom, because at this point we are just taking in pieces of evidence. Lavoisier lost his head and therefore had to stop doing his work, and then Proust picked up some more evidence by using the law of definite proportions. Remember, he was pulling apart water and said that every H2O has 2 hydrogens and 1 oxygen. And so all elements, or compounds, come in definite proportions. And he also did not have a model. We didn't actually get to agree that atoms exist all the way until Dalton came along. And what Dalton did is he wrote his atomic theory, where he said everything is made of atoms, and atoms are indivisible and indestructible. Atoms of the same element are the same. Atoms of different elements are different. And that compounds come in definite proportions. So he just re-said what Proust did. And he was the first of our discoverers to say that he thinks that an atom must look like a marble. There's no pieces, no parts, they're just indivisible little marbles. So we're now going to go on to 2 more scientists today. The next person that we're going to talk about, his name is J.J. Thomson. Okay. Thomson. And he's working about 100 years after Proust was. And he was working on whether or not these little pieces of marble and these little atoms are actually indestructible. And what he did was he worked with what's called the cathode ray tube. And I have a little video here to kind of show you what a cathode ray tube looks like. There is a little ray that you can see here. Okay. And, there's a little ray of particles, and what those particles are is he actually found that he could attract them with a magnet. And if you flip the magnet around, it would bend the ray back and forth, back and forth. And so he had to guess what he thought this ray of particles was. And what he happened to find, was the electron. Okay. He found the part of the atom that is negative in charge, because it was pulled when you had a positive end of the magnet and repelled when you put the negative end of the magnet. There's another very quick little video about how he kind of did his work.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the 2 metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons.
So, what he found were the electrons. And so now they said, all right, so Dalton is incorrect. They're not just marbles with no parts. They obviously have to have something negative about them. However, he's smart enough to know that we can't just have a whole bunch of negative little balls running around here. If you have a negative, you have to have a positive. So there must be something positive somewhere in order to equal out and neutralize all of these atoms. So what he decided was he came up with the plum pudding model. And if you've never heard of plum pudding, I had not myself. Plum pudding is actually a dessert that was very popular at that time, where it's kind of like a cake and then it has little plums in it. So apparently that inspired him to think that that's what an atom would look like. He thought that the cake itself was positive mush and that the little plums in it were the negative energy. So it's kind of, if I were to liken it to a today's dessert, I would think like chocolate chip ice cream, where the ice cream is positive and the little negative chocolate chips are negative. Chocolate chips are negative. So he had the plum pudding model, where the plums were negative little electrons and the pudding was positively charged medium. So if I were to draw it, he basically said that there was positive mush, okay, an atom has to be positive medium with little negative electrons scattered throughout it, kind of like chocolate chips in chocolate chip ice cream. So scientists ever trying to test theories and make sure that everybody is correct in what they're saying, we have another scientist came along, and he is very famous. If you've heard anything about the history of the atom, you probably have heard of Rutherford. Rutherford did what's called the gold foil experiment. So his name is Ernest Rutherford. He was working in the early 1900s. And what he did was he basically took a gun and fired it at a plum pudding, okay, or at a thing of ice cream. And so what he thought was going to happen is he had a very, very thin piece of gold foil, extremely thin. And he was going to fire alpha particles at it. And the idea is he was trying to support or negate what Thomson was saying. And he thought that if Thomson was right, so this is the plum pudding model right here, these should go straight through, okay? They should fire these little positive alpha particles and they should pass right through this positive mush with little negative pieces in it. Okay. So let's find out what he did. Here is a little reenactment of what actually happened with his experiment.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes...
So what you have happening here is that the gold foil is so thin that a lot of the alpha particles are going straight through, but a few of them are hitting something, okay? And he's about to tell you what it is. So, but when we expected everything to go right through, these alpha particles were hitting something in the gold foil. We're learning that there is something inside of the atom.
At a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics.
So let's break down what he said happened there. So basically what he discovered, Rutherford discovered the nucleus. And when he discovered the nucleus, he did the gold foil experiment. And so he thought that these particles were going to go right through the very, very thin piece of gold foil. But what actually happened was the alpha particles went through and actually hit something. So we know that Thomson is out, okay, and he was not necessarily correct with just the mush in there. What we have is we have this nucleus. And so a few things they found out from this experiment. So as their particles were zooming on through, they hit something and were scattered and thrown off course and things like that. So the first thing that they did, okay, so here's the conclusion, is that they found the nucleus. They missed the majority of the time. Majority of the time, the particles went right through and didn't hit anything. So if they missed the majority of the time, that means that the nucleus is extremely small in size, okay? The other thing is that they were firing positive particles at it, okay, and it was not getting stuck. So the nucleus itself must also be positively charged. And so that's where we kind of came up with the proton idea. There must be some positive charge inside of that nucleus. The last thing is that it basically stopped a speeding bullet. Okay, if you hit it head on, boom. That means it must be massive. So don't confuse massive with large. Okay, it's very small in size, but has a ton of mass. And you guys know from doing your calculations last week that all of the mass is found inside of the nucleus. Okay, perfect. So they needed a new model. Plum pudding is out. Plum pudding is not the way that we know how an atom looks. What we now have instead is that most of the atom is empty space. So what they changed to was that, hey, we have this teeny tiny little positive nucleus, positive, small, dense nucleus, and then most of the atom, okay, the electrons must be somewhere out here, but most of the atom is empty space. And they say that in a replica, if you were to take the pin or the end of a pen and hold that in the center of a football field, this would be the nucleus, and then the rest of the track going around the football field would be where the electrons are. So we are talking extremely small versus a ton of area for those electrons to be that are mostly empty space because the electrons have very little mass themselves. Okay, so now we went from the idea of an atom to evidence of atoms, then to the idea that maybe it's a marble. Then we went to, hey, we have negative and positive parts that must be looking like some some pudding with plums in it. And then we eventually found the nucleus here, which is tiny, dense, and positively charged. So make sure you do your lecture questions underneath this video. Have a great holiday, and we will see you back on Monday to continue our journey through the history of the atom.